name is Nur Siti Sarah binti Muhammad Suhaimi. So, what are you waiting for? Let's continue.
We are going to talk about classical mechanics and application of Newton's laws of motion in daily life. We must first shed light on the founder of these laws and the one who has the credit for bringing them out to us, which is Isaac Newton. Sir Isaac Newton worked in many areas of mathematics and physics. He developed the theories of gravitation in 1666 when he was only 23 years old. In 1686, he presented his three laws of motion. He established these laws to explain many physical systems and phenomena. Newton shows that these laws, in addition to the laws of universal gravitation, are able to explain capital laws of planetary motion, and these laws are still among the most important physical laws so far.
He was capable of being utterly tunnel-visioned and obsessed.
He's a massive contradictory figure.
And how the specific strategies that are useful in applying Newton's law of motion.
Assalamualaikum warahmatullah. My name is Nurzuri Iwani binti Hashim.
Once you identify the physical principle involved in the problem and determine that they include Newton's law of motion, you can apply these steps to find a solution. These techniques also reinforce concepts that are useful in many other areas of physics. Many problem-solving strategies are stated outright in the work example, so the following techniques should reinforce skills you have already begun to develop. The first step is identify the physical principle involved by listing the givens and quantities to be calculated. Second, sketch the situation using arrows to represent all the force. Third, determine the system of interest. The result is a free body diagram that is essential to solving the problem. Fourth and last step, apply Newton's second law to solve the problem. If necessary, apply appropriate kinematic equation from the chapter on motion along a straight line. Check the solution to see whether it is reasonable.
Hi and Assalamualaikum. I'm Nur Khadijah Khalila binti Muhammad Kaman. Now, I want to ask you, what do you understand about free body diagram? A free body diagram is a diagrammatic depiction of a single body or a subsystem of body that is separate from its surrounding and show off the forces operating on it. A free body diagram, or we call as FBD, is a graphical representation used in physics and engineering to depict the applied force, moment, and resultant reaction on a body under a particular state. They show a body or a network of body with all the applied forces, time, and responses that operate on the bodies. The body may be made of several interior components such as a truss, or it may be a compact body such as a beam. To answer a complicated issue, a sequence of free body and other diagram may be required.
When you step into an elevator, you feel like you are the same weight when you were waiting in the halfway. When you go up in an elevator, you will feel slightly heavier, and when you go down, you will feel slightly lighter, if only for a few seconds. If you were to stand on a scale in an elevator, your weight would standing stationary and going down. When you are stationary, your acceleration is 0, so the scale will only read your appearance weight. When the elevator is going up, through you are accelerating, which adds more force to the scale and increase your appearance weight. When the elevator is going down, the same is true, but the acceleration is negative, subtracting force from the scale and decreasing your apparent weight. So let's see what happens. First, let's take a look at the force in action as the elevator begins to move up.
Let's consider up as the positive direction. When an elevator starts to accelerate upwards, you and your scale experience the same acceleration. The flow of the elevator pushes you and the scale upwards. This means the scale has to push on the person with an extra force to push you and your weight up too. The new normal force is greater than just your weight alone. Let's add up the force acting on you. According to Newton's second law, the force acting on you are sum of F equal to ma. The overall acceleration is up, so the acceleration is positive. There are two forces in action, your weight down, negative mg, and the supporting normal force. Sum of F equal to n minus mg. N minus mg equal to ma. N equal to ma plus mg. N equal to m multiply a plus g. The scale reads the normal force, so it reports your weight as greater than it was at rest.
Now, let's look at the elevator accelerating down. We have set down the negative direction, so the sum of the forces are total forces is equal to negative ma. The same two forces are at work as when the elevator was accelerating up. Total forces equal to n minus mg. N minus mg equal to negative ma. N equal to mg minus ma. So n equal to mg times g minus a. The scale will read the normal force, which is less than it was at the rest.
Let's take a look about the elevator that we would draw if you were simply standing on the floor. We show a downward force of gravity and an upward normal force that is exerted on you by the flow of the elevator. These two forces balance one another to give a net force of 0 consistent with your constant velocity. Let's start by drawing a downward force of gravity and an upward tension force, which are the only force that act on the elevator when the elevator is empty. Even though we draw what looks like an empty elevator, to construct the free body diagram, we have to remember that in this case, you are in the elevator exerting a downward force on it. How do we represent this on the free body diagram? Newton's third law is helpful. If the elevator applies an upward normal force on you, then you apply a downward normal force on the elevator of exactly the same magnitude.
The third free body diagram, showing the forces acting on the system consisting of you and the elevator combined, is the combination of the first two free body diagrams. We have the tension the cable exerts on the elevator directed up and the combined force of the gravity acting on the system. When you combine the first two free body diagrams, you also get the upward normal force the elevator exerts on you and the downward normal force you exert on the elevator. By Newton's third law, the forces are equal and opposite, so they cancel one another when they are combined.
For this reason, as well as the fact that when we draw a free body diagram, the force we draw are expressed by objects external to the system we are considering. We don't include them on the free body diagram of the combined system. We could solve the problem by applying Newton's second law to the last free body diagram. The formula that we use is Fn equal to mg, Fn equal to mg plus Fn, Ft equals to weight of the second and third free body diagrams give the same result for the tension because we know Fn equal to mg from the first free body diagram. The conclusion is elevator is the most frequent pieces of equipment we use on a daily basis, and it provides opportunities for discussion of many mechanical topics and experiments. Now that we have established the foundation of dynamics through Newton's laws, we can apply them to a variety of physics to show how they would to us. Newton's law, as previously stated, applied in almost every physical. There are, however, a number of factors that frequently emerge. Our application will be limited to the following forces, which is normal forces, rotation forces, and tension forces. We'll be able to get the result of a range of physical events using these three very frequent forces.